Welcome! In this session, we'll explore a structured approach to solving algorithmic problems, using LeetCode number 1321 as our reference point. While the exact problem details are unavailable, we'll outline a general framework that you can adapt to handle similar challenges. Let's dive in. I currently do not have access to the content of LeetCode problem number 1321. Please refer to the LeetCode platform for the full problem description. If you can provide any details about the problem, I would be glad to assist further in creating a comprehensive explanation and examples for it. When tackling an algorithmic problem, the brute force approach is often the first to consider. It relies on systematically exploring all possible solutions to find the correct one. This method is straightforward since it simply iterates through every potential combination, permutation, or configuration of the input data and checks if each satisfies the problem's constraints. However, brute force comes with a significant trade-off. While it's easy to implement and can be used as a baseline solution, its computational expense grows rapidly with input size. For example, this approach often has a time complexity of n squared, or worse, making it impractical for problems with large datasets or strict time limits. Even so, it's a valuable starting point, particularly when you need to validate the correctness of your logic before diving into more complex solutions. An optimized approach builds on the foundation of the brute force idea but incorporates problem-specific insights to drastically reduce computational complexity. The goal here is to avoid unnecessary calculations by leveraging techniques like dynamic programming, greedy algorithms, or divide and conquer. For instance, dynamic programming focuses on breaking down problems into overlapping subproblems, while greedy algorithms aim to make locally optimal choices that lead to a global solution. Using auxiliary data structures, such as hash maps or heaps, can also speed up operations, and pruning parts of the solution space helps simplify the problem further. These optimizations typically result in time complexities like n log n, or m asterisk n, depending on the approach. While faster and more scalable, optimized solutions often require a deeper understanding of the problem structure and can be more challenging to debug and implement. In addition to brute force and general optimization, there are alternative strategies tailored to specific types of problems. For example, binary search is highly effective when working with sorted data or when narrowing down a solution space to find a specific threshold. Two pointers are useful for array or string problems, especially when searching for pairs or subsequences that meet certain criteria. Graph algorithms, such as BFS, DFS, or Dijkstra's algorithm, are indispensable for problems involving networks, dependencies, or traversals. Sliding window techniques shine in cases involving substrings, subarrays, or fixed-length segments, where maintaining an efficient window of data is key. Finally, backtracking is ideal for combinatorial problems, where you need to explore all possible configurations but can prune paths that fail to meet constraints early. Each of these strategies addresses unique problem characteristics, making them valuable tools in your algorithmic toolkit. The choice of strategy ultimately depends on the problem's constraints, the input size, and the type of data structures involved. For instance, if the task focuses on optimizing a sequence, dynamic programming might be the most effective approach. For searching within a sorted range, binary search is typically the go-to solution. On the other hand, if the constraints are loose, a brute force approach could suffice for correctness, even if not the most efficient. The key to identifying the right strategy lies in making observations about the problem. Noticing repetitive computations, spotting overlapping subproblems, or recognizing opportunities to simplify the solution space, such as through sorting or pruning, can lead to the critical aha moment. This understanding often highlights the trade-offs. While brute force is simple and reliable, it's computationally expensive. Optimized approaches are efficient but require deeper insights, and alternative strategies may strike a balance depending on the problem's nature. The decision to choose one strategy over another typically balances correctness, efficiency, and implementation complexity. For problems with large inputs or strict performance requirements, optimized approaches are usually the best choice, as they offer scalability. Conversely, brute force or simpler strategies may be sufficient for smaller constraints, quick prototyping, or verifying the correctness of a solution. Ultimately, the chosen method should align with the problem's specific requirements, the constraints imposed, and your ability to implement the solution effectively. By weighing these factors, you can ensure that the strategy you select not only solves the problem but does so in a way that meets its constraints efficiently and reliably. When approaching an unknown algorithmic problem, having a structured framework can make the process less daunting and more effective. The first step is to thoroughly understand the problem statement. This involves carefully reading the description and paying close attention to the input format, constraints, and output requirements. Ask yourself key questions. What types of inputs are being provided? Are they arrays, strings, graphs, or something else? What is the size of the input, and how does it affect performance? What constraints or conditions must be satisfied? For example, does the problem mention edge cases like empty inputs or extremely large values? Writing down a few test cases can help clarify your understanding and ensure you've captured the requirements correctly. This foundational step is crucial for building the right solution later on. Once the problem is understood, the next step is to explore brute force solutions. This involves starting with the most straightforward approach, exhaustively enumerating all possible configurations or states to find the answer. For instance, if solving a substring problem, you could iterate over all substrings and check each one. This step also includes analyzing time and space complexity to identify performance bottlenecks. Brute force solutions, while not always efficient, provide a baseline and can reveal patterns in the problem. These patterns can lead to optimizations, such as recognizing repetitive subproblems or overlapping computations. From here, you can begin breaking the problem into smaller subproblems or exploring algorithmic paradigms like dynamic programming, greedy techniques, or divide and conquer. For example, instead of recalculating sums for all subarrays, you might use Cadon's algorithm to find a maximum subarray sum efficiently. Selecting the right data structures is essential for simplifying operations and improving algorithm performance. For example, arrays are ideal for indexed access and sequential traversal, while hash maps or sets enable quick lookups or frequency counting. Stacks and queues are particularly useful for problems involving sequential processing, such as backtracking or breadth-first search. Graphs come into play for more complex problems like connectivity or shortest path calculations. Choosing an appropriate data structure can significantly impact the efficiency of your solution. After selecting the tools, the next step is implementation. Focus on coding the core logic incrementally, starting with correctness. Test your solution against edge cases, such as empty or large inputs, and use debugging techniques like print statements or assertions to validate intermediate states. For instance, in binary search, ensure the solution handles all possible positions of the target correctly, including when it's not present. If your initial solution does not meet the time or memory constraints, it's time to optimize further. Start by identifying performance bottlenecks and reducing the time complexity of the approach. For instance, a solution with O(n) squared complexity might be improved to O(n) log n by leveraging sorting or divide and conquer strategies. In recursive problems, replacing recursion with iteration can save memory, while techniques like memoization or caching can eliminate redundant computations. For example, in dynamic programming problems, storing intermediate results can drastically reduce the number of calculations. This iterative refinement process is driven by the problem's constraints. Smaller inputs may allow for simpler solutions, whereas larger inputs require efficiency. Testing remains critical throughout this step, as edge cases often reveal inefficiencies or errors in the refined algorithm. Data structures play a central role in problem solving, and understanding their use cases is essential. Arrays are well suited for sequential access, prefix sums, or sliding window techniques. Hash maps and sets excel in quick lookups, frequency counting, and eliminating duplicates. Stacks and queues shine in problems involving sequential dependencies, such as evaluating expressions or performing breadth-first search. Graphs are indispensable for connectivity and traversal problems and can be represented as adjacency lists or matrices depending on the specific requirements. By combining the right data structures with a structured problem-solving approach, you can systematically refine your solutions and account for edge cases effectively. This holistic method not only ensures correctness but also enhances efficiency, allowing you to tackle a wide variety of algorithmic challenges with confidence. The provided Python implementation solves a problem where you aim to maximize the profit derived from customer satisfaction in a restaurant setting. The array satisfaction represents the satisfaction levels of customers, where each level can positively or negatively contribute to the total profit. The main challenge is to determine the optimal sequence of customers to maximize the profit. The code begins by sorting the satisfaction array in descending order to prioritize the highest satisfaction levels first. This ensures that we consider the most impactful values early in our calculations. Two variables, max_profit and current_sum, are initialized to 0. Max_profit tracks the maximum profit obtained so far, while current_sum accumulates the running sum of satisfaction levels as we iterate through the array. In the loop, the algorithm evaluates whether adding the current satisfaction level S to current_sum will increase the total profit. If it does, current_sum is updated, and the profit contribution is added to max_profit. If not, the loop breaks, as adding further satisfaction levels would only decrease the profit. This approach is efficient, as it avoids unnecessary calculations once the contribution to the total profit becomes negative. The sorting step dominates the time complexity, resulting in an overall complexity of O(n log n), where n is the length of the satisfaction array. The space complexity is O(1), as the algorithm operates in place without requiring additional data structures. Overall, the solution is concise, efficient, and effectively handles edge cases such as empty arrays or arrays with all negative satisfaction levels. Here, we begin by importing the necessary Java utilities and defining our solution class. The main method, maximizeRestaurantProfit, takes an array of integers called satisfaction as input. These integers represent the satisfaction levels of dishes. The goal is to maximize the total profit by preparing dishes in an optimal order. First, we sort the satisfaction array in ascending order using arrays.sort. Then, we reverse the array to arrange the satisfaction levels in descending order. This ensures we prioritize dishes with higher satisfaction values first. The reversal is done using a simple loop, where we swap elements from both ends of the array until we reach the middle. Afterward, we initialize maxProfit to store the maximum profit we can achieve and currentsum to keep track of the cumulative satisfaction level. Next, we iterate through the reversed satisfaction array. For each satisfaction value, we check if adding it to the currentsum results in an increase in profit. If it does, we update both currentsum and maxProfit. However, if adding the current satisfaction value doesn't improve the profit, we stop the iteration as further additions will only reduce the total profit. Finally, the method returns the value of maxProfit, which represents the maximum profit achievable given the input satisfaction levels. By leveraging sorting, reversing, and early termination, we ensure the solution is both efficient and intuitive. This approach guarantees that we focus only on the most beneficial dishes while avoiding unnecessary computations. The algorithm effectively balances simplicity and performance, making it suitable for a variety of inputs. To solve this problem, we start by sorting the satisfaction array in descending order. This allows us to prioritize the values that contribute the most to the profit first, which is crucial for maximizing the result. After sorting, the array becomes 5, 0, -1, -8, -9. We then initialize two variables, max_profit and current_sum, both set to 0. The max_profit variable will track the highest profit we can achieve, while current_sum helps us calculate whether adding the next element is beneficial. In the first iteration, we take the largest value, which is 5. Adding it to current_sum gives 5, which is positive, so we include it. This updates current_sum to 5 and max_profit to 5. Moving to the next element, 0, we add it to current_sum, keeping the value at 5. Since this is still positive, we include it and update max_profit to 10. Then, we take -1, which decreases current_sum to 4 but is still positive, so we include it, updating max_profit to 14. However, when we attempt to include -8, the current_sum becomes negative, so we stop. The final output is a max_profit of 14. In this example, we consider the case where all satisfaction values are negative. The input array is -3, -2, -1, and we start by sorting it in descending order to get -1, -2, -3. Sorting ensures we analyze from the least negative value, which gives us the best possible chance for a positive contribution. Next, we initialize max_profit and current_sum as 0. Starting with the first value, -1, we calculate current_sum plus s, which results in -1. Since this is not greater than 0, we stop immediately. This tells us that no positive contribution is possible when all values are negative. Therefore, the max_profit remains 0, which is our final output. Now let's look at an example where all satisfaction values are positive. The input array is 1, 2, 3. After sorting in descending order, the array becomes 3, 2, 1. This sorting step ensures that we maximize the potential profit by prioritizing larger contributions first. We then initialize max_profit and current_sum to 0. In the first iteration, we take the largest value, 3. Adding it to current_sum gives 3, which is positive, so we include it. This updates current_sum to 3 and max_profit to 3. Next, we take the value 2, which brings current_sum to 5. Since this is still positive, we include it, updating max_profit to 8. Finally, we take the value 1, increasing current_sum to 6 and max_profit to 14. Since all the values contribute positively, the loop completes, and the final output is a max_profit of 14. The algorithm works by sorting the satisfaction array in descending order and iterating through it to include elements only if the current sum remains positive. This strategy ensures that we maximize the overall profit by considering the most impactful values first. By stopping the loop as soon as adding a value no longer improves the total profit, we avoid unnecessary calculations and ensure efficiency. Sorting plays a critical role in this process, as it prioritizes the highest contributions, making the solution both optimal and straightforward to implement. When analyzing the time complexity of the solution, we break it into two main steps. First, we sort the satisfaction array in descending order. Sorting an array generally has a time complexity of O, n*log n, where n represents the number of elements in the list. This is because sorting is a nonlinear operation and typically dominates the overall runtime. Second, we iterate through the sorted array. This involves a single loop that visits each element exactly once, performing arithmetic operations and comparisons in constant time per iteration. This contributes an additional O, n, to the total complexity. However, since O, n*log n, from the sorting step grows faster than O, n, it dominates the overall time complexity. Therefore, the time complexity of the solution is O, n*log n. Now let's evaluate the space complexity of the algorithm. The sorting step is done in place, meaning the input array is rearranged directly without requiring additional memory allocation. As a result, the space used for sorting is O1, ignoring the space required to store the input itself. Additionally, the algorithm uses only a few auxiliary variables, max_profit, current_sum, and the loop variable s. Since these variables do not depend on the size of the input, they consume constant memory, which is also O1. There are no additional data structures, recursion, or dynamic memory allocation involved. Thus, the overall space complexity of this solution is O1, making it very memory efficient. To better understand the efficiency of the solution, let's analyze its behavior in different scenarios. In the best case, if all elements in the satisfaction array are non-positive, the loop terminates immediately after sorting, as no further iterations are needed. However, the sorting step still requires O, n*log n, so the best case time complexity is O, n*log n. In the average case, the algorithm typically processes most or all of the elements in the loop after sorting, resulting in an average time complexity of O, n*log n. In the worst case, where all elements are positive, the loop traverses every element after sorting, but this does not change the overall time complexity, which remains O, n*log n. By comparison, a naive brute force approach would involve generating all possible subsets of the array, which has a time complexity of O2 to the power of n. Evaluating the profit for each subset adds another factor of O, n, resulting in an overall complexity of O2 to the power of n*n. The proposed solution is far more efficient, reducing this exponential growth to O, n*log n, by leveraging sorting and a greedy strategy. Finally, let's summarize the mathematical justification for the big O analysis. Sorting the array takes O, n asterisk log, n, and iterating through it requires an additional O, n. When combining these two steps, we add their complexities, O, n asterisk log, n, plus O, n. Since O, n asterisk log, n, grows faster than O, n, the total time complexity simplifies to O, n asterisk log, n. For space complexity, no extra memory is allocated beyond the input array and a few auxiliary variables, keeping it constant at O, 1. This efficient use of time and space ensures that the solution is optimal for the given problem, with a time complexity of O, n asterisk log, n, and a space complexity of O, 1. When solving problems, it's important to be mindful of common mistakes that can trip you up. One frequent issue is misinterpreting the problem constraints. For instance, forgetting to account for edge cases like empty inputs, single-element arrays, or maximum values can lead to incorrect results. A common example is assuming the array is sorted when the problem doesn't explicitly state it. The solution here is to carefully read the constraints and test your code on edge cases, such as an empty list or extreme values. Another pitfall is overcomplicating the solution by jumping to advanced algorithms without first considering if a simpler approach, like brute force or a greedy method, might work. Starting with a naive solution can help you understand the problem better before optimizing. Additionally, while correctness is important, writing unoptimized solutions can lead to failures on larger inputs due to timeouts or memory issues. This is why analyzing the constraints and aiming for feasible time and space complexities, such as O, n, or O, n log n, for larger inputs, is critical. Lastly, neglecting edge cases in recursion or iteration can cause major issues, like runtime errors or infinite loops. Always explicitly handle base cases in recursion and ensure your loop variables are updated correctly to avoid these mistakes. Another common mistake is the improper use of data structures. For example, using a list where a set or dictionary would be more efficient can significantly slow down your solution. To avoid this, always consider the operations you need and choose the appropriate data structure, like using dictionaries or sets for O1 lookups. Beyond avoiding mistakes, there are some key strategies that can help you during interviews. Recognizing patterns is essential. Techniques like sliding windows, two-pointers, dynamic programming, or divide and conquer often recur in algorithmic problems, so becoming familiar with these can give you a significant advantage. Also, remember to optimize iteratively. Start with a brute force solution to build understanding, then refine it step by step. Interviewers value the clarity of your thought process, so communicate clearly. Share your assumptions, trade-offs, and reasoning aloud, even if you're uncertain about the optimal solution. Finally, always test your solution extensively. Use edge cases and stress cases to ensure your code is robust and handles all scenarios correctly. To deepen your understanding, it's helpful to explore related problems. For example, LeetCode 1.2 sum is a classic problem that highlights the use of hash tables and two-pointer techniques. LeetCode 1.21, best time to buy and sell stock, uses a single-pass algorithm to find the maximum profit. LeetCode 76, minimum window substring, is a challenging sliding window problem requiring careful handling of boundaries. And LeetCode 198, house robber, is a dynamic programming problem with constraints on adjacent selections. When approaching problems, you might also consider alternative strategies. Brute force is a great starting point for small input sizes or when you're trying to understand the problem, though it may fail for larger inputs due to high complexity. Greedy algorithms work well for optimization problems where local choices lead to global solutions, but always verify with counterexamples to ensure correctness. Divide and conquer is useful for breaking problems into independent subproblems, such as with merge sort or binary search. Dynamic programming is ideal for problems with overlapping subproblems and optimal substructure, though you should watch out for space complexity or redundant computations. Finally, sliding window and two-pointer techniques are especially effective for subarray or substring problems, but be careful to adjust boundaries correctly to avoid errors. Great job! We wrapped up our discussion with a structured approach to solving algorithmic problems. Remember to practice these techniques regularly and apply them to a variety of challenges. Thanks for tuning in, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!